All right, let's keep going with similarity reasoning here. It can be a little bit challenging when two triangles have the same shape but not the same size. So we'll get into a little bit more about proportionality and how we can test for it in this lesson. Exercise 1 to test whether two fractions are the same, whether we do have the same scale factor. One way to do it that can work easily for you is to just test the cross products. If the two cross products are equal, then we do have proportionality, and if they're not, then we don't. So testing in part A, we get 9 on one diagonal and 6 on the other. Not true. Second problem, part B, we get 60 on both, so we're good. And the third one, we get 105 on both, so we're good. So it's called product of means equals product of extremes, but you can think of it as cross products. So that is how we can use cross products to test for proportionality. In exercise 2, the diagram has lines AD and BC and BE intersecting at point C, and they are. We also have parallel segments from AB and ED. So because of those given pieces of information, we can mark our vertical angles, we can mark our two alternate interior pairs, and we have our diagram marked up for similarity. Now, which two triangles are similar? It's asking you, the challenge isn't to find the triangles, there's only two of them there, it's to name them correctly. So you can name triangle ABC however you want, but then the other triangle needs to match it. So if you say A first, then you have to say D first, because those are the equal angle pairs. You also would go from B to E, and then C and C would be last. So just make sure that the vertices are matching up when you're naming your similar triangles. To write down the reasons for these statements, BC and CE are the same scale factor as AB and ED, because corresponding sides of similar triangles are proportional. So we wouldn't say congruent, it's not CPCTC. We have to say corresponding sides are proportional in similar triangles. And then finally, we can do these products by you can say product of means equals product of the extremes. What you'll see me write in class for something like this often is cross product. So as soon as you say similar triangles with one of our codes, the next line is typically going to be to establish a proportion that contains the segments we're trying to prove. And then finally, we'll change it to a cross product to show whatever product we're trying to prove. So you'll see an example of that. But these are the reasons that we use following similar triangles. Once triangles are similar, we use these two reasons to work with the segments. All right, so in this proof, here's an example. We're trying to prove that these two cross products are equal. Okay, so in order to do that, we have to locate the triangles that contain those segments, and then we have to essentially write a proportion that contains those segments in fraction form, because after we do that, then the diagonals will lead us to this product. So if we look at the diagram with the two triangles, we can see that the given information is that we have parallel lines. And so because we have parallel lines, that tells us that we have equal angles at 1 and 2, corresponding angles. We also have a shared angle at angle M, so we can say reflexive property there. And we then, after 3 lines, we have enough to show that those triangles are similar by angle. Again, we need to be careful to get the order right. So if we go MNP on the first one, we want to start at M again on the second one and go to Q and R so that everything matches up. So line 4 has our similarity code. And then from there, to decide which sides to put into our proportion, because remember, there are 3 pairs of sides that could be proportional here. So to decide which ones to use, we want to go back to what we were trying to prove and make sure that our fractions contain these segments. So if I need MQ and I locate MQ is going to go with MN, and so that's going to be one of my fractions. And I also need MR in my product, so I go to MR and put it over MP. Nowhere in this proof statement did it say to do anything with QR or NP. So therefore, those sides, even though they are proportional, they don't need to end up in the proof at all, because I'm not asked to prove those. So my fractions contain only the segments that I need, and then the cross product takes me to what I was trying to prove. So for line 5, you write corresponding sides are proportional. Line 6, you can just write cross product. You don't have to write out the whole sentence if you don't want to. All right, moving on. Recall that an altitude is a segment drawn from the vertex perpendicular to the opposite side. When we do that, we end up getting a set of right triangles that will all be similar to each other. And that's what we're going to try to prove here. So what's happened here is we started with right triangle ABC. An altitude was drawn from B out to AC and made another right angle here. If you need to turn your paper to see it better with B on top, you can do that. But from any vertex, you can draw an altitude to the other side. So once that's been done, now we want to explain why ADB must be similar to ABC. All right, well, triangle ADB is this small one here, and triangle ABC is the full original right triangle. Both of those triangles contain angle A. They also both have a right angle. So whatever angle A is, maybe it's 30 degrees, maybe it's 50 degrees, whatever it is, it's going to be the same in both triangles. And clearly 90 degrees is the same in both triangles. So we have, through angle, we have a pair of similar triangles, the little one with the outer one. So to draw it with the same orientation, all I want to do is take triangle ADB and reflect it so that it looks like triangle ABC. Same orientation means make it look the same. All right. And so now what we can see is that there are corresponding sides. AB corresponds to AD, and AC corresponds to AB. So that segment AB occurs in both triangles. However, in the original large triangle, it's a leg. In the new triangle, it's a hypotenuse. So it corresponds to different segments. So when I go to write my proportion, this first fraction, AC over AB, is a hypotenuse fraction. And the second fraction, AB over AD, is a leg fraction. In both fractions, the larger segment is on top and the smaller segment's on the bottom. But both fractions are matching up corresponding sides. So once I've done that, now I can do a cross product and show that AB squared is equal to AC times AD, because that cross product will be the same. All right, so if we're trying to show a proof for why that's true, you can think of it as AB times AB and AC times AD, and notice that nowhere in that is it asking for anything about DB or BC. So after I show that my triangles are similar, I then write my proportion using only the sides I need and do the cross product diagonally. And we end up with what we're asked to get.